Hello everyone, welcome back to our channel. Today, let's dive into the amazing world of sound. Ever wondered how we hear things? Why some sounds are high-pitched while the others are low? Or what makes your favorite music sound so good? Stick around and we'll uncover the science behind it all with some fun experiments. Sound is everywhere. But what is sound? It's a type of a wave. Let's break this down. Sound waves are called longitudinal mechanical waves. That sounds fancy, I know, but it just means that sound travels as vibrations through air, water, or even solids. Here, let me show you. Even though the speaker isn't directly touching the smoke particles, it's still affecting their movement. The sound waves travel through the air, creating vibrations that disrupt the flow of the smoke. But how are the waves involved here? Sound is a mechanical wave, which means it needs a medium to travel, like air or water. Let me prove it. Here, I have a bell in a jar. Right now, we can hear it ringing. Hear that? Now I am going to remove the air from the jar using this pump. It's silent. That's because there's no air inside for the sound to travel. Cool, right? Now, let's break down how a sound wave works. Imagine a speaker playing music. The speaker's diaphragm moves back and forth, creating vibrations. When the diaphragm moves forward, it pushes the nearby air molecules closer together, and when it moves backwards, it pulls them apart. This back and forth motion continues, passing energy from one group of molecules to the next, creating a wave that travels through the air. Eventually, these vibrations reach our ear. The moving air molecules cause our eardrum to vibrate, sending signals to our brain, which interprets them as sound. If we could see this movement, it would look like a longitudinal wave, with areas where molecules are compressed, which is called a compression, and areas where they are spread out, which is called a rarefaction. This is how sound travels. Wavelength. This is the distance between two consecutive compressions or rarefactions. If the sound has a longer wavelength, it means the pitch will be lower. A shorter wavelength means a higher pitch. Frequency. This is how many compressions pass a point in 1 second. We perceive higher frequencies as higher pitched sounds like a whistle and lower frequencies as deeper pitched sounds like a drum. Pitch is essentially the way we experience frequency. Higher frequency is higher pitch and lower frequency is lower pitch. Amplitude. It represents how tightly the compressions are packed. We perceive the loudness of a sound based on the amplitude of the sound wave. The larger the amplitude, the more energy the wave carries and the louder we hear the sound. Essentially, loudness is our way of experiencing changes in the amplitude of sound waves. Here, we have a microphone that converts sound into electrical signals, and this device, the oscilloscope, helps us visualize those signals. Watch what happens when I speak louder. The amplitude of the wave increases, meaning the waves appear taller on the screen. Now if I whisper, the amplitude decreases and the waves become smaller. Wave speed. This is how fast the compressions and rarefactions travel through the medium. Now let's talk about time period. Time period is the time it takes for one full compression and rarefaction cycle to pass. Shorter time periods mean higher frequencies and longer time periods means lower frequencies. What does all this mean when you hear it? If we change the frequency,
you'll notice the sound becoming higher
or lower. Increasing the amplitude makes it louder. So from these pointers, we can even find the speed at which the sound travels. For example, any object or phenomenon moving at a constant speed, we can write speed is equal to distance by time. Now apply this to a wave. In one cycle of the wave, the distance traveled by the wave is one wavelength, and the time taken for one cycle is called the period. So, we can write speed of wave is equal to wavelength by time period. Now, frequency is the number of cycles per second and the period is the time for one cycle. Frequency and period are inversely related, that is, f is equal to 1 by t. Substitute t in the earlier equation and simplify to get this. For example, if a sound has a frequency of 500 Hz, which means 500 sound wave moves through a point in a second. In a wavelength of 0.68 meters, its speed is 500 into 0.68, which is equal to 340 meters per second. That's about how fast sound travels in air. Yes, I said in air, because the speed of sound varies depending upon the multiple factors including medium. How does the medium governs the movement of sound? In solids, particles are tightly packed and closely connected. This means that when a sound wave causes one particle to vibrate, it quickly transfers that vibration to the next particle and so on. Imagine a row of tightly packed balls. If you push the first one, the energy is quickly passed on to the next, causing a fast chain reaction. Now, imagine the balls are spaced far apart. When you push one, it takes longer for the energy to transfer to the next ball. This is similar to sound traveling in gases, where particles are farther apart, causing a delay in energy transfer and making sound travel slower. You can check this phenomenon with a simple experiment. First, place your ears flat against the table, like this. Now, have a friend lightly tap the other end of the table with a spoon. Listen carefully. Did you hear the sound through the table first? Now, lift your head and listen again as they tap. Compare when you hear the sound. This is the same reason why, in old movies, cowboys put their ears on train tracks to hear a train coming before it arrives. Sound travels much faster through the metal rails than it does through the air. Now, any change in the behavior of the medium also affects their speed of sound, such as temperature. When temperature of a substance increases, its kinetic energy also increases, which in turn makes the molecules move faster, thus increasing the speed of sound. Similarly, humidity, or the amount of water in the air, also affects the speed of sound. More water vapor makes the air less dense, causing the sound to move faster. That's it for sound today. We learned how it travels, what affects its speed, and more. Stick around for the next one. More fun science coming your way. See you soon.